All right, so 5.3.
Now,
the real zero. Because of time, we are probably not going to get to theorem of bounds, zeros, and intermediate value theorem. If you go to pre-cal or if you take pre-calculus, then we'll let your pre-cal teacher worry about that. Remainder theorem. So using the remainder and factor theorems, how do they work? So starting off with division algorithm polynomials. When you divide polynomials, you divide them like you divide whole numbers, right? So if you remember that, then yes. So you're dividing, you're going to have a remainder. So you're dividing, you're going to have a remainder. You have your dividend. Your quotient, your dividend, your divisor, your quotient, and your result with a remainder. So you write it just as if you were dividing a whole number, right? So if you remember for dividing a whole number, you divide, you multiply, you subtract, bring down. Does that sound familiar? Divide, multiply, subtract, bring down. Divide, multiply, subtract, bring down. It's the same thing for polynomials. Okay, so for example, when you divide, what the remainder theorem is saying is that you can determine if it's going to be a remainder or not by substituting in that value into the function. The x minus 2. So we're going to look at this. We're not actually going to divide x cubed minus 5x squared minus 6. We just want to know is if it's divided by x minus 2, will there be a remainder? The first thing you do is you take the factor and set it equal to 0. By doing that, I get that x equals 2. We did most of this last year.
Well, I specifically.
I'm glad. I'm going to teach you this. X minus 2 equals 0, and then you get x equals 2. Then the second thing is you're going to substitute that into the equation. So you're going to find f of 2. So I'm going to substitute f of 2 in. I get 2 cubed minus 5 times 2 squared minus 6.
I get 2 cubed minus 6. This gives me 8 minus 5 times 4.
Oh, what happened?
I don't know. A lot of things.
5 times 4 minus 6. I have 8 minus 20 minus 6.
This gives me negative 12 minus 6, which equals negative 18.
So my remainder would be
negative 18. That's the remainder. Okay? I'm going to pause and let you do it on B, and then we'll go over it. Cool. So first step is to take the factor, set it equal to 0, and you should have gotten x equals negative 4, right?
Yeah.
Second step is substitute in. So you have negative 4 to the third minus 5 negative 4 squared
minus 5 times negative 4 squared minus 6.
Still with me?
Yeah.
So that gives us negative 54.
Negative 54.
Is that right?
Is that right?
Did I do that math right? 64. I didn't even say 54.
Minus
5 times 16 minus 6. So negative 64 minus 80 minus 6. And that gives us negative 150. Be careful with your negatives. How do we feel about the remainder theorem? Good? Good. Remember it a little bit?
I didn't mean to write the screen twice.
All right, now. The key thing about remainder theorem is it ties into the factor theorem. The factor theorem feeds off the remainder theorem, saying that if you end up with 0, that means that is a factor of your polynomial. Does that make sense? So if I end in 0, that means no remainder,
then that factor is
a factor of the polynomial.
Okay?
So again, if you substitute it and you get a remainder of 0, that is a factor of the polynomial. Cool? And vice versa. So for example, if we check these, so now we have x minus 2. What?
So now we have x minus 2.
Did we already do x minus 2?
Yes.
Sorry, so it'll be x plus 2. We did minus 2 already, right? Okay. No, that's right. This is a whole different problem, y'all. I remember what I'm doing in my life. I'm right. All right, so we're going to do x minus 2, which means that we are substituting in what value? 2, right? 2, right? So we're substituting 2. Gives me 2 to the third minus 2 times 2 squared plus 3 times 2 minus 6. That's 8 minus 8 plus 6 minus 6. Which is what? 0. So what does that mean about x minus 2? It's a factor. Yes, it's a factor. Makes sense? Because we ended up with 0. Now, if we do x plus 1, so I'm substituting in f of negative 1. And be careful with your negatives. I have negative 1 cubed minus 2 times negative 1 squared plus 3 times negative 1 minus 6. It's going to be negative 1. A negative is a positive. So plus 2 and minus 2. Plus 2. And minus 2. Minus 3 minus 6. So I have negative 3 minus 3 minus 6, which equals negative 12. What does that mean? Not a factor. Not a factor. And that is how the factor theorem works. Do you see the difference between being a factor and not being a factor? You have a remainder that's not 0. Cool? All right. Why do I have it twice? I don't know. Who knows? All right. Now we're on to our numbers of real zeros. Real zeros. Okay. Polynomial function cannot have more real zeros than its degree, right? So what that is saying is if I'm a degree of 3, what's the most number of factors I should have? 3. Right? 3. I'm a degree of 5. The most factors I should have is 5. But I can't have less than that. So we can use the Descartes rule of signs to determine the number of positive and the number of negative real zeros of a polynomial function. So the degree lets us know what's our max amount, right? And then Descartes rule lets us know how many positive and negative numbers are working with. Got it? This is new, by the way. All right, so this really smart person says that suppose that f is a polynomial function written in standard form. The number of positive real zeros of f either equals the number of variations in the sign, and by variation it means you go from positive, from subtracting to adding, subtracting to adding, or else equals the number less an even integer. Or else the number of negative real zeros of either equals the number of variations in the sign of the non-zero coefficient of f negative x, or else equals that number less than the even. It's better to just see it. We're just gonna all right, so here we have this function. F of x equals 2 x to the 6 minus 3 x to the 4 plus x squared plus 5x minus 2. Agree? All right. So that's our polynomial. Because of the polynomial, its degree is 6. Its max number of real zeros is 6. Agree? Because it is a degree of 6. Now to determine whether the numbers are, its real zeros are positive or negative, comes from this rule. Since there are 3 variations in signs, by variations in signs, it says I changed signs here. I went from positive to negative. And then I went from negative to positive, and then I went from positive to negative. Those are 3 variations in signs. Can you see that? So therefore, we expect either 3 positive real zeros, or 1 positive real zero. So out of the 6 possible real zeros, out of the 6 possible, we think that one or two things. Either 3 of them are going to be positive numbers,
which means that the other ones are negative, or only one is a positive number. Because the rule is it's that number of change or 2 less than the number of changes. And we had how many change in signs? 3. And 2 less than 3 is 1. Okay. Then there are 3 variations in signs. So we expect either 3 negative real zeros. So then the other option is 3 negative real zeros or 1 negative. So then now we look at this, we know that the graph of f has either 3 positive x-intercepts or 1 positive x-intercept, and 3 negative x-intercepts or 1 negative x-intercept. We don't know anything else about it, but we do know this, and that's all we can conclude from this start. Okay, and the reason being is that when you look at this, the 3 positives, that's saying that there's multiplicities, right? So there's potential multiplicities at 3 numbers. And 1 positive means that it's just 1 big number and a lot of multiplicity at 1 value. And that's all this part wants you to know. Is analyze and make predictions. Not a whole lot more there. So for example, if this was if I only had 2 changes in signs, so if I only had 2 changes in signs, that means 2 possible, right? And then 2 minus 2 is 0, so then there only have to be either 2 positives or 2 negatives. It's always minus the 2. Now, how does the man figure this out? I don't know. You can go read his papers. But it's a lot of time to recognize that pattern, I feel. Some dedication right there. But yeah, that's it. So, use the rational zeros theorem to list the potential rational zeros of polynomial function. Does saying P over Q ring any bells? I say P over Q?
No.
None?
No.
Maybe if you see it.
A little bit.
A little bit? All right, so when we're talking about rational zero theorem, it's saying that you can create a list of potential real zeros by taking the factors of the constant, so the factors of your constant, and dividing by the factors of your leading coefficient. That's our P over Q. P represents the factors of our constant, and Q represents the factors of our leading coefficient. And that's our rational roots theorem. And that's how we find our potentials. So for example, we have 2x to the 5th minus x to the 4th minus x squared plus 4. So this is my constant, so this is my P. This is my leading coefficient, so this is my Q. So the factors
of 4 are
plus or minus 1,
plus or minus 2, plus or minus 4. Agree?
Agree.
Those are the factors of 4. The factors of Q of 2 are just simply plus or minus 1 and plus or minus 2.
I don't remember this.
All right. So then your potential zeros are dividing each one of these. So 1 divided by 1 is 1, right?
Yeah.
So plus or minus 1. That's a potential number. Then 2 divided by 1 is 2. 4 divided by 1 is 4. And then I do the same thing I did with 1. I'm going to do with 2. So 1 divided by 2 is 1/2. 2 divided by 2 is 1. Don't need to write it again. 4 divided by 2 is 2. Do I need to write it again? No. So these are all of my potential zeros.
I can
I can hear you. I'm sorry.
I think at 1.5 again.
1 divided by 2. Oh, sorry. So you divide each number and the numerator by each number in the denominator. And so these are my potential zeros. After we have potentials, then we'll use synthetic division. So we need to be comfortable finding the potentials. How do we feel about finding potentials? You list out the factors and divide. List out the factors and divide. Yes? Does that sound doable? If not, speak now so I can help you.
I don't know.
Okay, which part?
The factors. How did you get the numbers?
What numbers multiply to make 4? 1, 2, and 4. These are my factors. What numbers multiply?
4?
Yes. 4 is a,
You just do it off whatever else you
So your P, your constant, and your leading coefficient.
Oh, I see.
Constant and your leading coefficient.
Oh,
Yeah, your factors. Numbers that multiply to make that.
And you divide the top.
And you divide the top with every number at the bottom.
That's like,
And that's how all your potentials come about.
now it makes sense.
No problem. Want to make sure. Because we need to.
right now?
Huh?
Is that it?
Yes, because the bell's gonna ring. And so we're gonna use the potentials tomorrow to then do some synthetic division. Yeah. All right.